Getting into the assignment, spreadsheet drag problems. All right. So use the web for unit conversions unless you enjoy doing the math. Doubt anybody does, but maybe there's somebody. And you should open up at least one of these two spreadsheets here to solve these problems. Probably get away with just one. All right, number 1, 0.1 kilogram egg drop vehicle, drop from a height of 7 meters, blah, blah, blah. I'm supposed to find the drag coefficient of the egg drop vehicle. So if this is just dropped, I could use either of these spreadsheets. I think I'll just use the one with the X and Y velocity input. So opening this up, and I'm going to make a copy. $11, $14. I've got so many copies, I just want to tell them apart. I don't want to mess up the original one there. The first thing I'm going to do is set up all the parameters in these yellow cells. I'll leave G alone. The direction, that's being calculated. Ooh, I should have made that purple since it's being calculated. That's confusing me. So I'll go back and fix that later. X and Y velocity, these are my inputs. So this is something being dropped. The initial X velocity is 0 and the initial Y velocity is 0. The mass is 0.1 kilogram. The the air density is 1.24. Cross-sectional area, I don't give you that. I tell you it's a square cross-sectional area, and each side of the square is 0.1 meters. So the area of a square that's 0.1 meters is 0.1 squared. So it's 0.01 square meters. Drag coefficient is what I'm looking for. I'm going to be guessing and checking with that. Starting time can be 0. That's all good. Really doesn't matter what the height is that I'm dropping this thing from. Or does it? Yes, it does. So I'm dropping it from 7 meters and it's hitting the ground in 1.26 seconds. So it very much matters. Y should be 7. Initial X, I'm just going to leave that at 0. So it tells me that the fall time is 1.26 seconds. And this is saying the time aloft is 1.28 seconds. So it's staying in the air too long, which means the drag coefficient's too big. So let me bump this down to 0.9. Takes a while because there are 12,000 rows here. Time aloft is now 1.2745. I'm going to go down to 0.8. Time aloft is now 1.6 or 26525, so getting closer. 0.7 for the drag coefficient. 1.256. I've gone past it, so let's try 0.75. And that's close enough. So 0.75 is the answer to number 2. Now, what is the terminal velocity? We've already got it calculated right here. It's 14.517 meters per second. So this just calculates it based on this stuff, the air density, cross-sectional area, drag coefficient, and mass, and all that stuff. So that's really, that should be negative because it's down. What's the terminal velocity at the moment the velocity at the moment it hits the ground? So I know it hits the ground at 1.26 seconds. So I'm going to go down until time on the bottom left says 1.26. Now, alternatively, I could just look at the Y position column, column L, and I could go down until column L is at 0, which is going to be right about that time that I just mentioned. Past it. Going up, up a little more. And they may not match perfectly because of the way my spreadsheet's set up. But anyway, right here. Looks like we're going from Y position positive to negative there at 1.26 seconds. And the question is, what's the velocity at this time? If I look at Y velocity, it's essentially negative 10 meters per second. So there's the answer to 1C, which is also numbered number 4, which is unfortunate. All right, number 5. Now we're dealing with the skydiver. 60 kilogram skydiver in head down position. Reach terminal velocity of at negative 59 meters per second. What's their cross-sectional area? So I could do a bunch of stuff here. This calculates terminal velocity, whether or not I put in any actual velocity. So I'm not even going to mess with the initial x and y in the beginning. I'm just going to put in the other bits of data. So the mass of the skydiver is 60 kilograms. The air density, we're told, is now 1.23. The drag coefficient is 0.7 because they're kind of tucked. It would be higher than that if they were arms are spread out. And we know that the terminal velocity is negative 59 meters per second. Now, if I look at this terminal velocity over here, that's 369. That's too fast. That's because I'm using the same cross-sectional area that I put in for the egg drop vehicle from the previous one. So that needs to increase. And in fact, what we're doing right now is figuring out the cross-sectional area of the person. So let me try 1 meter, see what happens. Terminal velocity is 36.9. No, that's too slow. We're going for 59. So in order to make it a little faster, I need to decrease the cross-sectional area. Let's try 0.8. Getting there. 0.5. Closer. I'm going for 59, but I'm at 52. 0.4. 58. Pretty good. Need to go a little faster, so a little less cross-sectional area. 0.392 is what I'm going to try. Oh, by the way, these problems tell you to set time increments to 0.005. I've already got them set there. I should put that in 2A as well. Actually, no, it doesn't matter. The time increments don't matter for this. So there, terminal velocity is right about 59 when the cross-sectional area is right about 0.392. That is the answer to number 5. But what does that mean? How big is that actually? So what we need to do is convert that to feet. I'm just going to click on this and copy it and Google it. Convert square meters. Yeah, I've typed it before. It knows what I want to do. So put in the square meters. 0.392, that's 4.22 square feet, basically. So you can imagine that. A little bit bigger than a 2x2 square if you took all their cross-sectional area and made it into a square. So that is the answer to 6. Now, number 7, when the parachute's fully open, the drag coefficient is 1.2. I'm going to switch this to 1.2. Nope, 0.2. And the terminal velocity when the parachute opens drops to 6 miles per hour. And I need to figure out what the area, cross-sectional area of the parachute is. So that's meters per second. 6 miles per hour, what's that? All right, let's go back to Google again. Convert miles per hour to meters per second. And you know how to do this. You could just divide by divide by 2.24. But I'm going to get a very precise answer. So 2.68224 meters per second is what I want to arrive at here. And I do that by making the cross-sectional area bigger. So let's go to 1. Okay, 28 meters per second. Let's go to 10. 8.92. Let's go to 20. 6.3. What I'm going for, remember, is 2.68. So I kept doing this, and I think I got 111. 111 square meters puts me at 2.679, which is pretty close to 2.68. Close enough. So that is the answer, number 7. And number 8 asks you for the diameter of this in feet, because I want you to be able to visualize how big this thing is. 111 square meters. It's hard to tell what that is. So how do I do that? I guess I could do that over here. So and then we'll check. So the area of this, assuming that this is a circle, is pi r squared. And pi r squared equals 111. So I want to find out what r is, and I'll get the diameter from that. So I'm going to do equals 111 divided by pi, and then I'm going to take the square root of all that. And I could do SQRT in front of it, or I could do to the second. Nope, no, that's not the square root. Square root is 0.5. All right, 5.94. And let me just check that. So pi times this squared equals 111. So that's meters. I need to convert that to feet now. So convert, excuse me. Get rid of that email. I'm going to copy that and convert meters to feet. So 19.5 feet. I'll copy this, and I could do it in my calculator, but I'm going to do equals 2 times that, because that was the radius. So the diameter is 39 feet. There's your answer, number 9. Number 10 asks, if the parachute suddenly opens, so suddenly you're going 59 meters per second, which let me just tell you what that is. Go back to miles per hour to meters per second. I can go this way. 59 meters per second is 131 miles per hour, so that's really fast. Let's say you're going that fast, you're an ordinary skydiver kind of tucked, and suddenly, instantly, your parachute is 39 feet across. That doesn't happen, but if it did, what drag force would you and the parachute experience? So the way we need to do this is now I do need to put in a y velocity, and I'm going to make that negative 59. So now down at the bottom, if I hit enter, give this a little time, I have all these calculations. And right here's the drag force. Let's see, that's 285,156.558 newtons of force from the drag. And the net force is only slightly less than that because weight is pulling the parachuter down, but the drag is so much stronger. So that's the answer, number 9, 284,568. And then number 10 asks you to convert that to pounds. So let's just have Google do it. Convert newtons to pounds. 64,105 or 106 pounds of force. That's reminds me of the calculations of what would happen to Santa Claus if he really did deliver all those presents. I think that would just kill anybody. So that's the answer. 64,105. And then number 11 asks, why would you not actually experience that force? Well, it's because the parachute doesn't open to its full diameter all at once. It unfurls. That slows you down a little bit. It starts to get bigger and bigger and bigger, so you don't experience that. Although it is a really big force, and for what I hear, it's the hardest part of parachuting on the body when that parachute opens. Finally, number 12 or 2H, if it did open instantly, how long would it take to slow the skydiver down to 6.1 miles per hour? So remember, the terminal velocity is 6 miles per hour. So 6.1 is almost there. How long would it take to get there? Convert miles per hour. to meters per second. Let's put in 6.1. See what we're looking for. 2.72694 seconds. So the way I figure this out is I keep an eye on y velocity. So right down here. And I'm trying to see how long I have to go down to get it to 2.72. So let's go down, down. Oh, I've already passed it. 2.7. No, I didn't pass it. 2.72 what? 2.727 or 694. Somewhere right around here. So 0.6315 seconds, less than 1 second to slow down to that speed if your parachute immediately opened to its full extent. But that, again, that doesn't happen. And if we wanted to actually get to terminal velocity, the terminal velocity of, let's say it is negative 2.67, 91621, 16211. Let's look at a little more of this. It says here I would just have to, I would take about, oh, yeah, somewhere around 2.92 seconds. In reality, theoretically, you'd never really get there. If I had decreased these time increments, made them really small, the closer you get to terminal velocity, the less acceleration you experience. So you accelerate more slowly the closer you get to it, which means you get to it more slowly. So theoretically,